I want to go over a topic that is actually much later in our coursework, but it is a topic that does show up both on the Calc AB and BC test, and it's very easy to understand. So I figured it was a nice one to kind of be a starter video. It is called L'Hôpital's Rule. I know it sounds like the hospital's rule, but it's actually a mathematician's name. His name was L'Hôpital, and it's a way to evaluate limits. And a lot of times, limits, because we learn them so early in calculus, can be something that it's hard to remember exactly what we did. So, what I want to start with is a little bit of a review. So, I have the notes on the screen so that you can see those while you're hearing my voice. I'm not going to go through everything that's on my normal notes, just the things that I think are helpful to work on any calculus problems. So, with our limit review, when we're taking a limit as we approach some constant, we had two techniques that we used. We could do direct substitution, which was basically just plug in the number. So, if you're trying to approach 3, you plug in 3, get your answer. I'm going to make this a little bit bigger so you can see it a little better. Then the next option, if direct substitution doesn't work, is to try to use some sort of algebra. There's a lot of algebra techniques you can take. Probably the one that you're most comfortable with, the one that I like the most, is factoring, because that allows you to see where the discontinuities are in addition to evaluating the limit. So if you look at the algebraic approach, limit as we approach 3, when we try to plug 3 in initially, we can't because we get 0 on the top and bottom. But if we factor and cancel, we essentially cancel the problem. We call that a removable discontinuity because we remove the whole. And then we try to plug in 3, then we can evaluate the limit. So those were things that we did back in pre-calculus, chapter 1 type of problems. Then we had something called limit guidelines. These were working with limits that went to either positive infinity or negative infinity. And these were ones that we were looking at the degree and where the degree was bigger, top, bottom, or the same. We did this in chapter 3, so it's a great review for the chapter 3 material. So if the limit was going towards an infinite value and the degree was bigger on top, we got an infinite answer. If the degree was bigger on bottom, we got 0 because the bottom essentially takes over. And if the degrees were the same, which is the most common type and usually the easiest, we use the leading coefficient ratio. So that's what's on the right side where it says guidelines. Well, L'Hopital's rule gives you a way to evaluate limits, either if there's not algebra that you remember, or there's not algebra that you can do. So maybe something you can't factor, or maybe something that you have to rationalize, and nobody really likes to rationalize anyway. So it gives you an alternate approach. So here's what his rule says. So it's focusing on what's called an indeterminate form. And an indeterminate form means you either get 0 over 0 when you try to evaluate it, or infinity over infinity. 0 over 0 is the common. And with that, and it kind of goes through here of what makes it indeterminate. I'm not that concerned that you understand how to prove that it's indeterminate. I care that you understand what to do if it is. So here's his rule, and I'll give you a chance to take a look at it, but I think explaining it makes a whole lot more sense than just reading the words on the page. So, what this is saying is if you try to evaluate a limit and you do get either 0 over 0 or infinity over infinity, we can apply his rule, which said that we could take the derivative of the numerator, the derivative of the denominator, and try again, try to evaluate that limit again. Whatever answer we get will be the answer of the initial limit. This is not a quotient rule. You're not doing any sort of deriving with the entire numerator and denominator. You're actually looking at each of them separately. Again, makes a lot more sense if you can see some examples. So here are my examples that I normally do in class. I have other examples that I'm going to put out on a PowerPoint that you can take a look at, give you some other opportunities to try on your own, but at least this gives you a starter. So if you look at this first one, the one that says homework number 7, which obviously I'm not giving you that homework anymore, this was one that if you try to evaluate the limit as you go to 3, if you put 3 in, you do get 0 over 0. Now, the algebra person would tell you then you have to rationalize. I hate rationalizing, so here's another option. The other option is you could take the derivative of the top. It is a chain rule, so power out front, power 1 less. Derivative of what's inside is just 1. The derivative of the bottom is just 1. That's why I just put a 1 there. Clean that up a little bit. Now try to plug 3 in, which is what we were evaluating. And if you put 3 in now, you can get an answer that is not indeterminate. You get 1/4. That is the same answer as you would get if you would to rationalize this instead. Second one, same thing. You could factor and cancel this, but let's say you just have a moment where you can't remember how to factor, or heaven forbid you don't like factoring. This gives you another option. If you put 2 into your original limit, you do get 0 over 0. So you take the derivative of the top, which is very easy because it's just a polynomial, derivative of the bottom. Now plug 2 in, you get 3 over 1, which is just 3. Where you see that this becomes a necessity is when you're working with things that are not algebraic. So, exponential functions, trig functions, logarithm functions are all really good examples of when this could be used. So, with this one, when I put 0 in, I get 0 over 0. The derivative of the top is 2e to the 2x, derivative of the bottom is just 1. Now I try to put 0 in, e to the 0 is 1, so I end up giving a limit of 2. There's not algebra for this one, so you can't fix it a different way. This is one where you'd actually be forced to use his rule, and it works really simply. Same thing with this number 4. The natural log as you go to infinity gets bigger. So that is infinity. The bottom is infinity. Take the derivative of the top, derivative of the bottom. Now, when you put infinity in, anytime your bottom is getting bigger and your top's not, that's going to go to 0. And that is your final answer. It is possible to repeat his rule more than once. So you can, I call these repeated applications of L'Hopital. Essentially, every time you try to evaluate it, you keep getting something indeterminate. The moment you get something that's not, is when you're done. You can't, you're not allowed to overuse it. So if you get an answer that is not indeterminate and you decide to keep going because it's easy, you would end up working yourself into a mistake. So here, number 5 is a great example of this. So is number 6. When I originally evaluate it, I get infinity over infinity. So I take the derivatives of the top and bottom, still get infinity over infinity, still get infinity over infinity. And it's not till I've gone through this process multiple times that I finally get something that's not indeterminate. Because down here, I no longer have an infinite value on the top. I have a 6 on the top divided by something that's going to infinity. That would be 0. Another way to think of this is to look at the original problem and think what's growing faster. Exponential functions, e functions, will always grow faster than polynomial functions. So your denominator will have to get bigger faster. So there is actually a shortcut to know that this is 0, but L'Hopital kind of proves it. Same thing with this one with number 6. When I put 0 in, this is actually a one-sided limit. It wants to know what happens to 0 from the right. The nice thing about L'Hopital's rule is it doesn't matter if it's a one-sided limit or an overall limit, it still works. So when I put 0 in from the positive side, I get 0 over 0. Take the derivative of the top and bottom, I still get 0 over 0. Take it one more time. This time I don't get 0 over 0. E to the 0 power is 1. The bottom is going to be a really small number because you're putting something in that's really close to 0. Multiplying it by 6 is still close to 0. As the bottom shrinks and the numerator stays the same, you're going to get something that gets bigger and bigger and goes to infinity. That's not an indeterminate form. That's actually the answer. I want to show you just one more. Trig is actually a pretty common way that this shows up, and they usually work with trig functions like sine and cosine because they're the easiest to derive. So with this initial one, the sine of 0 is 0. You should know that. When you take the derivative of the top and the derivative of the bottom, you get 6 cosine 6x over 2. Cosine of 0 is not 0, it's actually 1. So you get 6 over 2, which is 3. I actually see, when I look on AP test, you tend to see trig and E ones more than anything else. So I wanted to give you a chance to hear my voice explaining it, not just look at a sheet of paper. There are other indeterminate forms you can see on the bottom. They are not things that show up on the AP test. I usually just do that as an extra topic. Not going to do that now. I think this is enough. So hopefully this explanation allows you to feel comfortable with going through and trying some on your own. I'm going to give you a Delta Math to see if you're comfortable with it. I also have some extra videos that you can watch if this wasn't enough. But hopefully this is enough of a quick lesson that makes sense to you. I miss seeing all of your faces. Definitely more fun with an audience, but I hope you are all well, and this makes life a little easier with the assignment that I asked you to do.